talking about modeling a disk galaxy with cosmological simulations.
Okay, thank you. So I'm going to talk about the results of some simulations that we've run as a part of my thesis project, and then this is using cosmology simulations to sort of study the growth and evolution of supermassive black holes and galaxies together. But sort of the first results are just focusing on the galaxy itself. So also, this work was done, as you mentioned, with my advisors, Nick Ganaden and Andrew Hamilton, who's at Colorado still, and Andrei Kravtsov at the University of Chicago. So since the title was from Megaparsecs to Milliparsecs, I'm going to start out by just clarifying what the typical kinds of things are that you find on each of these scales. So on megaparsecs, this is really starting to refer to cosmological scales. This is where the biggest objects in the universe are. So this is like the size of a cluster or something. So this is really getting into the large scale cosmology stuff. On kiloparsec scales, this is where you find sort of the scale of individual galaxies. And on parsec scales, we're getting into structures within the galaxy. So for example, the circumnuclear disk of the galaxy, which is mostly what I'm going to be talking about. And then down on the smallest scales, getting down into milliparsecs is where we find like the scale of the accretion disk around a supermassive black hole. So we sort of, in the simulations I'm going to talk about, we come down and then sort of stop just short of the accretion disk, which I'll explain later. So I'll start out by explaining why you might want to use cosmological simulations to study supermassive black hole growth and where this sort of fits into the picture of galaxy evolution. I'll describe the details of the simulation that we use and what our approach is, how we get the resolution that we get. And then I'll give some results, so the properties of the simulated galaxy and some of our interpretation of what we find. So one motivation comes from the desire to understand how different classes of galaxies or of AGN, how they relate to one another. So there's this sort of classic example of Seyfert galaxies, which is a good way to start. So basically, when you observe Seyfert galaxies, you see thermal emission from the AGN. So there's a component from the AGN, and this is just thermal emission from the accretion disk in the center. You also see infrared emission coming from this dusty sort of molecular region close to the center. And then there are broad and narrow emission lines coming from clouds, which are moving quickly also in the center. So the closer in the cloud is, the broader the line because it's moving more quickly, right? So when Seyfert galaxies were observed, there were sort of two classes of objects that were seen. There was one where you see both the broad and the narrow emission lines. And in one class of objects, you don't see the broad lines, which are the clouds that are closest in. So it was proposed that this is actually an orientation effect. So in one class of object, the type 1 objects, you're actually looking into the center, so there's nothing sort of blocking your view. And so you see both the narrow and the broad emission lines. And in the type 2 class of objects, you're actually looking through this dusty molecular structure, which is blocking some of your view of the center. So you see the narrow lines from the clouds that are farther out, but you don't see the broad emission lines. So you can sort of infer from the ratio of type 2 versus type 1 objects what you expect the geometry of this sort of molecular dusty region in the center to be. And it was sort of originally proposed that you have this dusty torus. So if you hear of the AGN obscuring torus, that's what this is referring to. But whether or not it's actually this toroidal structure is sort of open for debate. But either way, we know that it should be relatively thick because of the population of type 2 versus type 1 objects. So that sort of raises the question, what allows this structure to get so thick? So it could be supported by hydrostatic pressure support, or it could be something like hydromagnetic disk winds coming off the accretion disk, which are sort of puffing up clouds that are sort of inflowing in the midplane of the galaxy, and that's what gives you this thick toroidal region. So if this is the case, that sort of connects the geometry in the center of the galaxy to the evolution of the galaxy a little bit, because the more material you have accreting, the easier it is to make this structure. And if you have the AGN in the center, which is sort of blowing its way out of the middle to give it maybe this classic toroidal structure, then that ties it to what the AGN is doing as well. So these things are all sort of connected. So that leads to the question whether, well, first of all, there are type 1 and type 2 analogs in brighter types of AGN. So Sieverts are sort of low luminosity AGN. But there are also type 1 and type 2 analogs in other AGN. And so the sort of, so whatever is causing the torus maybe brings in this idea of an evolutionary picture, and you might extend that to other kinds of AGN as well. So not just the structure in the central region, but maybe some of the things that are different between different populations of galaxies are also evolutionary effects, like sort of this classic idea of disk galaxies merging together and making a big red elliptical or something like that. So in all of these cases, the sort of different stages of the galaxy evolution, or of what the AGN is doing, are sort of, well, so the different stages of the galaxy evolution are evident in the type of AGN that you observe. So the AGN is sort of telling you what's going on in the galaxy at different times. So AGN feedback not only traces black hole growth if AGN are driven by accreting supermassive black holes, but it also plays a potentially important role in galaxy evolution as well. So we know from other observations that supermassive black hole supermassive black holes and their host galaxies probably co-evolve. So, for example, the properties of the bulges of many galaxies are correlated to the mass of the supermassive black hole at the center. So there's this sort of famous one that's the M-sigma relation that I show here. But there's also relationships between like the mass of the black hole and the mass of the bulge or the brightness of the bulge. And these are all potentially manifestations of sort of the same relationship. It's not immediately clear which one is the most fundamental relationship. But so the two are either connected, the galaxy and the black hole are either connected just simply because they're assembled at the same time. So they sort of undergo the same cosmological history. But it's also possible that the two are interacting with one another through AGN feedback. So AGN feedback is potentially providing the link between the growth of the galaxy and the growth of the black hole. Okay, so we come back to this basic idea that AGN are driven by accreting supermassive black holes. So that's sort of tying everything together. So why do we care about AGN? Well, I've already talked a little bit about how they might play an important role in galaxy evolution, but specifically they could do things like halt star formation, or if they're not effective at that, they're at least halting their own growth and helping to sort of develop these relationships with the rest of the galaxy. The amount of energy potentially available in the form of AGN feedback is huge, at least at high redshift where you have more AGN. So this is sort of an optimistic estimate, but still, there's a lot of energy in AGN feedback, and it's not clear how much there is because we don't really know what the efficiency of AGN feedback is in the real world. So, but if the efficiency is significant, AGN feedback could potentially influence the distribution of matter on larger scales. So not just within the galaxy, but in the environment of the galaxy as well. We see evidence for this in clusters, for example, where AGN heat up the intracluster medium. So AGN are important, probably, likely. So it's important to understand AGN fueling. We want to know how gas even gets into the vicinity of the AGN to keep it going. So how gas gets from large scales to subparsec scales in a galaxy. We also want to know how long fueling episodes occur for, whether it's a continuous thing or whether it's episodic. And how is the fuel continuously provided, or are there other things going on in the galaxy that are sort of competing? Like, for example, star formation. So if you have stuff sort of falling toward the center, but then it all turns into stars before it gets there, then you don't necessarily have a lot of gas left over for feeding an AGN. So just to go over some of the ideas about fueling mechanisms, so there are sort of large-scale mechanisms that are responsible for some of the feeding, at least at very high redshift. So, for example, major mergers are important at high redshift where they happen more often. And in this case, you have large-scale gravitational torques in galaxies, which help to drive angular momentum outward, allowing stuff to fall in. Maybe not all the way in, but it allows stuff to fall in at least to the central few hundred parsecs of the galaxy, where you might have some other process take over the rest of the way. Bar instabilities might be useful in this regard. So in this case, you have sort of a large bar in a galaxy, whether it's a stellar bar or a gaseous bar. But this can create a gravitational torque that drives matter inward as well. And for example, in the case of bars within bars, which is a mechanism proposed by Isaac Schlossman and collaborators, you have sort of a large-scale bar which funnels material inward, where it then sort of halts, but then becomes unstable again and forms a secondary bar, which takes gas all the way in to the central tens of parsecs or so. And then you can have other processes that take over, like viscous transport and things like that. So these are different proposed mechanisms that may occur in different populations of galaxies or in conjunction with one another as well. There's also secular evolution of galaxies, so not necessarily where you have two big galaxies merging together, creating all these large dynamical disturbances, but galaxies evolve on their own as well. So there's sort of the slow accretion of gas into galaxies just from their local environment. And there's also internal evolution inside galaxies. So this is, as galaxies are living, they slowly develop these instabilities like spiral waves or bar instabilities. These can do things like build pseudobulges in galaxies or maintain star formation or maybe even continue to feed a supermassive black hole. So these are processes that may be also important at low redshift where you don't have as many things like major mergers going on. So simulations have tried to follow some of these ideas. So for example, large-scale simulations, or for example, cosmological simulations, will do things like follow mergers between halos and include sort of prescriptions for feedback in individual galaxies in order to try to reproduce things like black hole demographics. So sort of in this example on the right-hand side here, this is from a recent simulation by Di Matteo et al., where they sort of put in all of these halos with seed black holes. Well, actually, there's hydro in the simulation too. So they put in all of these black holes into the simulation and sort of follow mergers and put in prescriptions for feedback and things like that, and then sort of measure the black hole demographics, so sort of the black hole mass density as a function of time. And they find that it actually matches observations quite well. They're able to reproduce sort of the local black hole mass density. And there are other sort of smaller but also large simulations where they do things like merge together two blue young disk galaxies, and at the end you come out, I guess it's kind of hard to see the colors, but at the end you come out with sort of an elliptical galaxy that's got a red older population of stars, which is sort of what we expect from observations. And these simulations also are able to reproduce things like the M-sigma relation fairly well. So on the other end, you have smaller simulations too. So galaxy scale simulations, and here I'm referring to the central kiloparsec and smaller. And in these simulations, you do things like follow the evolution of a gas disk, sort of an isolated gas disk. And here, for example, this is a simulation by Keiichi Wada where they simulated a disk on a scale of a few hundred parsecs, so with better resolution. And they find things like this multi-phase supersonic turbulent ISM that develops because this disk becomes self-gravitating and stuff starts to collapse, and that's what causes this filamentary structure. So these are places where you might find star formation sort of in the disk. So whether you're talking about these large cosmological simulations where you put in feedback and follow mergers and do all this stuff, or whether you're talking about sort of simulations of the circumnuclear disk in a galaxy all the way down to the accretion disk, it's sort of clear that there's a large range of scales that are important to understanding galaxy evolution. So how they interact with their environment and how the environment affects the galaxy, but also you need to understand the physics that are going on inside of the galaxy too. So ideally, if you want to combine the two things, you want to have some kind of adaptive technique. So what we've done, we've used the adaptive refinement tree code, which is written by Andrei Kravtsov and collaborators. And this is an adaptive mesh refinement code. So what that means, in case anyone's not familiar, instead of just having a big cosmology simulation with enormous resolution everywhere, that would be incredibly computationally expensive. So in adaptive mesh refinement, you can have finer resolution in regions where you need it and coarser resolution in regions where you don't. So here's kind of an example where I've overlaid a mesh on top of just a picture of a galaxy to show, in the center of the galaxy here we have this fine resolution, and then on the outside much coarser resolution in the lower density areas. So specifically the code that we use, the ART code, calculates the gas hydrodynamics on an adaptive mesh like this one, which allows a large dynamic range. So going from sort of supergalactic scales all the way down to the edge of a supermassive black hole accretion disk covers a range of sort of 10 to the 8, a dynamic range of 10 to the 8. The code also includes dark matter and stellar particles, and the stellar particles differ from dark matter particles in that they form at an observationally motivated star formation rate, but they're also capable of producing feedback. So they inject energy and metals into the ISM. Although actually the run that I'll be talking about today, we sort of wanted to start simply, so we actually turned off the feedback in the high resolution portion of the simulation. And then also the gas cooling is covered by using rates tabulated from the cloudy cooling code so that they're density, temperature, redshift, and metallicity dependent.
Excuse me?
Yeah.
How many phases do you follow the ISM? The warm, hot, cold, molecular phase, or just parts of it?
If you're using cloudy, it's just
We-
all, it's continuous.
It's a continuum phase. And that means you also have prescripts for molecular physics?
Yeah, So there is stuff being added right now to the code that includes some of that,
These
but I think.
simulations are not actually, so you stop at 10 to the 4 basically, because everybody has so far at least.
Oh, I think it 10 to the 4 what temperature?
Yes.
No, it goes lower than that. I think like 100 or something.
You're
I think.
just putting in a metallicity, right?
Yeah.
And using cooling rates, you pull out a table from cloud.
Yes.
So that includes the molecular physics, delta physics, all that.
Yeah. But we aren't actually following that stuff here. We're just using the rates from cloudy, I guess, is what.
You're using a lookup table essentially, right?
Yeah.
You tell the density and metallicity and the flux of photons. You put in a spectrum of light or not?
Well, so there is a radiative transfer capability in the code, which was run in the cosmological simulation, but actually I've turned it off here, so there's no.
So if you then follow metallicity, do you have a metallicity-dependent cooling function as well? Or?
Well, that comes out of cloudy. But what do you put in for the heating for the gas?
Well, that also comes from cloudy, right?
Well, cloudy,
There's-
the way you work is you put in a radiation field, like putting in a radiation field. The answer, I guess, is no, right?
We're not putting it in from the simulation, no. I guess is that what you mean? Like,
Yeah.
we're not putting it in from the simulation. The only thing we put in from the simulation is, the density and the temperature, which I guess is sort of cyclic.
Well, but how you get into temperature, I guess, is the question. What's the energy source?
The stars emit energy. So we just put in some energy rate some typical energy rate from supernova, for example.
Okay, so you're just dumping in energy in some unspecified manner. And then
Yeah.
you're calculating the cooling rate using cloudy. Fine, okay.
Yes.
So it's all of it. Basically, do you
So-
also follow it in metallicity? Do you enrich any gas successively once you form stars?
We do enrich the gas when we're forming stars. So we put in sort of a fixed amount of metallicity depending on how often stars go off or whatever. So I should mention here before I talk about the actual simulation. But so there's sort of two phases to the simulation that we ran. There's the cosmological part, which is sort of what I use as the initial conditions, and that was run with all of this stuff, with the stellar feedback, which is where we get the metals and the heating and everything, and the radiative transfer. And then the part that I ran with the really high resolution, where we sort of zoom in, which I'll talk about in a minute, we turn those things off. So it's sort of, they started in there as initial conditions, but then later on I don't put them in. So, but there are plans to put them in eventually. So
you're on a short time scale, basically, you're on high resolution simulations.
yes, yeah.
When you say from the large scale, you are using feedback, you just dump energy into the gas, depending on the local population of stars.
Yes, yeah. So okay, so maybe I can explain some of that with this next part. So this is, now I'm going to talk about the initial conditions, so the cosmological simulation. So what was done, So I suppose by Andrei Kravtsov, he ran this initial cosmological simulation from very high redshift, just from your standard, cosmological initial conditions with periodic boundary conditions. Ran it all the way to redshift 0 in order to identify the most massive halo in the simulation. And they found, a halo massive enough to host a sort of typical L-star galaxy at redshift 0. So then they traced this backwards and reran the cosmological simulation with high resolution. So by high resolution here, I mean 9 levels of refinement, which corresponds to about 50 physical parsecs at redshift 4. That's the number that I have. So reran it with the high resolution, sort of centered on this halo to resolve the development of this galaxy. So then what I do is I take that simulation and just run it again, but at different redshifts, but with very high resolution, so increasing the resolution in the simulation to go all the way down to subparsec scales. Okay, so what we do, so on the sort of larger scales, so here now by larger scales, I'm talking about sort of the finer scales in the cosmological simulation. So in the vicinity of the galaxy, the gas density is lower than what we expect to find in the center of the galaxy if we're going to zoom all the way into the center. So the dynamical time is much longer. But in the center of the galaxy, we have very high densities and so a shorter dynamical time. So we don't want to just immediately increase the resolution everywhere because then we're limited by the dynamical time on shorter scales. And what we want to do is develop sort of this quasi-stationary state on each level because we didn't initially resolve the simulation all the way down to the smallest scale. So we want to reach some sort of quasi-steady state so that the sort of inner parts of the simulation are really just fed by the boundary conditions with the larger simulation. So what we do is we actually zoom in slowly. So we force the simulation to resolve at this sort of lower resolution for 100 dynamical times until it reaches this quasi-stationary state. And the 100 was sort of an experimentally determined number. We ran a few different simulations to see what worked. And then we allow it to increase one more level to the next level of refinement and force it to evolve again for 100 dynamical times. And we keep doing this on each level, so forcing it to reach this quasi-stationary state on each level before allowing it to refine to the next. And we put in this more aggressive refinement to get it to refine when we want. So we do this stepping all the way down. But on this level, the time steps are shorter. So it makes sense to go slowly because if we immediately zoomed all the way into here, well, one, we'd have these sort of transient effects from zooming in all the way all at once, but two, the time step would be very short, so it would take a much longer time for these scales to reach a quasi-stationary state. So that's why we do it slowly. And then once we get all the way to our maximum resolution, so we go all the way to 20 levels of refinement here, which corresponds to about 0.03 parsecs per cell at redshift 4. That's physical. So once we get to the maximum resolution, we just let it continue to evolve for a few 100,000 years, which takes a long time because the time steps are so short. So just sort of a summary of the zoom-in process. So we begin with this cosmology simulation, which contains a typical galaxy. Increase the maximum resolution one level at a time so that it reaches this quasi-stationary state on each level before we go to the next. And then after we reach the maximum resolution, what we do is we actually replace a fraction of the gas in the center with a black hole particle, just to sort of trace where the center is. But this black hole particle actually isn't doing anything at the moment. And our galaxy at this stage of its evolution is so gas-rich, it's got so much gas in the center of the galaxy, that this particular black hole mass that we chose, so 30 million solar masses, is negligible at our resolution. The gas dominates the gravity. And then we continue to evolve this simulation for several 100,000 years.
Even at the final resolution, 0.03 parsecs, that's pretty small.
Yeah, so the mass of the black hole is actually comparable to like the mass in the central cell of the simulation in 1.03
so
cell.
Compared to like our galactic center, it's way different.
Yeah.
Much more gas rich, I guess.
Yes.
And also, are you sure there's enough time to reach these steady states on these large scales before the smaller stuff kind of kicks in? It seems, wouldn't you kind of, I don't know, it seems a little counterintuitive. Maybe we'll talk more about it.
Yeah, so I think so, because the evolution doesn't change very much once it reaches the quasi-stationary state. So things don't, well, also because the time step is smaller, but yeah, it doesn't, things on the larger scales don't really change much once they get, so we reach this density profile, which I'll show, and it maintains this density profile over the entire evolution of the simulation. And we sort of determine the point at which it reaches this profile is the point at which it reaches this quasi-stationary state. So, okay.
The only indications to try to get to nuclear density is when it starts cooling, it'll cool faster and faster, I think. And so it tries to get to really high density.
Yeah, so sorry, what was the question? Do we have anything to stop it, or?
Yeah, is there any way to stop that?
Well, so we impose a maximum resolution, so it's not gonna fragment any further, and we impose a few different criterion on the maximum level of refinement. So one, there's this artificial pressure support, and also we try to meet the genes criterion, which avoids artificial fragment or just numerical fragmentation in the code. So I think these things sort of keep it from wanting to go further than level 20. So it sort of stops it at our resolution, I think. Does that answer your question? Or the resolution we want? Potentially in some places. So maybe I'll come back to that later on, or you can remind me too when I get to. So, okay. So here is just to give you an idea of what the simulation looks like. So this is volume rendering of the gas density on different scales. So the ruler bar at the top here shows the scale in kiloparsecs. So that ruler bar is 250 kiloparsecs across. And here, this scale is the gas density in particles per cubic centimeter, I think. Okay, so 250 parsecs, you can see sort of the large scale structure. And then here, zooming into the scale of the galaxy, here we're on a scale of 5 kiloparsecs. You can see the spiral waves, at least in the gas. This is just gas, not stars. Well, the stars are there, but I'm not showing them. Okay. Here's the circumnuclear region of the galaxy. So getting into, this is 250 parsecs across. And if you can see it, you notice here that the density scale has changed because the density is getting so much higher as we go toward the center. Also, this dot in the middle is just to mark the location of the center, and that's also where the black hole is. But it's not that big. And here, this is on a scale of 25 parsecs, and you can start to see lots of structure in this region. And the smallest one that I'll show here is a scale of 2 parsecs. And here, if every cell in this box were at our maximum resolution, each cell would occupy sort of 1 pixel in this image. So that shows you how good the resolution is in the center of the galaxy. I think the region that's actually at the maximum resolution, that was just right in here. But just to give you an idea of how small those cells are. Sort of neither. It's a transient thing. So there's, I'll show a time movie also, but there's waves and lots of other things going through the disk. We haven't tried yet to really resolve the structures in the center or to model them and describe them, but that's something we're going to do soon. Okay, and I'm not going to talk a lot about the stars, but just to give you an idea of what they look like. So here they are, and I've colored them with 2 different colors. So yellow is supposed to show the oldest stars in the galaxy, and blue shows the younger stars, just to show you that they do sort of lie where they're supposed to. So the younger stars are primarily in the disk, and the older stars are more isotropic, making up a bulge in the galaxy. And this is on a kiloparsec scale. As is this, and this is again showing the gas density, but just so you can see a face-on and an edge-on view to see just how thin the gas disk is. And in the bottom panels, I'm showing the gas temperature, which is a little hard to visualize because it's so mixed. But this is just to show that primarily this disk is cold. It's mostly cold molecular gas, but there are hot cells in the interior that are kind of mixed in, but it's a little hard to see. And this happens from gas that's sort of falling perpendicular to the plane of the galaxy, which gets shock heated as it falls in. But also, there are all these waves moving through the disk that are there's all this supersonic turbulence too. And so individual cells in the disk get very quickly heated to high temperatures, and then they cool very quickly because the cooling time is so short. So the average temperature actually remains low, but there are these sort of localized hot pieces in the disk.
So if you go back to the slide where you showed
This?
that one there. So like in that inner, either in 250 parsec one or the 2 parsec one, or what are the surface densities of gas in there?
The surface density?
Yes.
Oh,
'Cause those are clearly flattened structures, right? They still have spiral arms. So the relevant numbers is surface density. I'm just wondering if you know where the mass is inside of 20 parsecs or whatever.
so the mass inside. So I guess I know the mass. I used to have a mass plot in this talk, but I took it out. So there's something like, I don't know, like a few billion solar masses of gas in the center of the galaxy. So I know inside a kiloparsec there's like 10 to the 10, a few times 10 to the 10 or something. But
So if you put that much gas inside a kiloparsec, the gas is now, if it's dusty, which it is, because you have probably getting up for solar metallicity.
yeah, well, so it's high redshift. So I guess it's a little less than solar, right?
Well, it depends.
Yeah.
If you look at quasars at redshift 6, they're super solar.
Okay.
So, but the reason I'm wondering is because you're using the cloudy for cooling.
Yes.
So when you get those kind of surface densities, the cloudy assumes optically thin gas.
Yes, that's true. So that's something we're working on right now, is to include optically thick cooling in the center of the galaxy. So that's actually, I mentioned we didn't try to sort of resolve and model the structure in the center, like to look for a torus or something like that. And that's because we weren't including optically thick cooling, but we're adding that to the code now and going to try to do the center with more.
But even at 100 kiloparsec, I mean, a kiloparsec is still, that's not so much to say, but you can do the same physics there.
To account for? Yeah. Yes. So that's sort of the very next thing that we're going to do. Okay, so here's the gas density profile, which I mentioned. So here, the lines on the top are the gas density. So this is just to show that it follows this power law to very high precision. So if you can't see the different colored lines, that's okay, because that's kind of the point. But this black line here, the solid black line, is a time average version of the gas density profile. So this is averaged over like 500,000 years or something like that. And then the green and I'm not sure what color the other two lines are sort of snapshots of the gas density profile, one at an earlier time and one at a later time. And that's just to show that the profile doesn't change very much over time from the average. So also the dashed line is this r to the minus 8/3 power law, just to show you what the slope is. And then the dashed lines on the bottom, these are just sort of as an aside to show the dark matter and the stellar density profiles. And we haven't looked into this in great detail, but actually the slope sort of in this central circumnuclear region of the dark matter and stellar density profiles does seem to be consistent with models of adiabatic contraction in galaxies. So, but other than measuring the slope, we haven't looked into that much further. But it's a possibility. Okay, so as far as the velocities in the disk, so I mentioned before that it was supersonic, so it's actually highly supersonic in the central few hundred parsecs. The disk is also cold, which you can see from the sound speed and also from the temperature picture that I showed. But these sound speeds correspond to less than 1,000 Kelvin, so this is really molecular gas. And I should also mention that all of these profiles, they're mass-weighted averages, and they're calculated over spherical shells, so it's a spherical average, actually. So, but actually this, the mean sound speed was computed to ignore those, ignoring those super high temperature shock-heated cells, because they have the effect of raising the temperature so that the mean is not necessarily indicative of what's going on in the disk. So, but these are sort of typical temperatures. VT, so VT is the rotational velocity. Yeah. Well, it's just it's the tangential component of velocity, which is approximately the circular velocity in our case. It's not because, So I guess it can be shown that for different sort of geometry disks that the circular speed is not exactly sort of the Keplerian speed, so they don't, but it's close. It's the same slope anyway. Okay, so we have this cold, self-gravitating molecular gas disk, which is rotationally dominated. And these kinds of disks are susceptible to fragmentation. So they can develop bar or other sort of global non-axisymmetric instabilities. They can develop spiral waves, and also local instabilities, which can lead to gravitational collapse. So we looked at various criteria for stability in our disk. So I'll explain what each of these are, just to try to get an idea of how stable the disk is. So in the top panel here, so this is the ratio of the rotational kinetic energy to the potential energy of the galaxy. And so this is sort of a criteria proposed by Ostreicher-Peebles, and it refers to a specific sort of geometry in galaxies, but nonetheless it's an indicator of stability, although some people don't necessarily believe that it's that useful, but we looked at it nonetheless. And these dashed lines here, these are the criteria for stability for both secular and dynamical instability above this line. So we measure for our disk, and we find that we're above both of these criterion. So that indicates global instability. But it's questionable how applicable this criterion is to our galaxy. So we also look at another useful stability criterion, which is the Toomre-Q parameter. And sort of the standard way of using the Toomre-Q parameter is for, it describes linear instability, but for axisymmetric perturbations, if Q is greater than 1, then the disk is unstable. So there's also kind of this region of marginal stability, sort of somewhere between Q of 1 and Q of 2 or something like that. Or sorry, it's the other way around. So stable is Q greater than 1 and unstable is Q less than 1. And this region of marginal stability between Q and 1 and 2 refers to stability against non-axisymmetric perturbations as well. So in this region, you might be stable for axisymmetric perturbations, but not for non-axisymmetric. And so we find that our disk lies somewhere in between here. So it's sort of stable, sort of not, conveniently. So you can also try to estimate the scale of the instability just using the dispersion relation for waves in the disk. And you can estimate the fastest growing or most unstable mode for the axisymmetric case, and also for the case which includes non-axisymmetric perturbations. So those two are shown here, and then just sort of for reference is the critical wavelength of stability. So anywhere that your scale is, on scales greater than this line, than these lines, the disk is unstable. So we find that our disk is unstable, and it's unstable on a range of scales. This is actually lambda over r. It's on a range of scales, but those scales are not that small. They're an appreciable fraction of the size of the system. So that leads us to believe that the disk is globally unstable, but it might be sort of locally stable.
When you calculate stability, are you using the velocity dispersion?
Yes. So we add the velocity dispersion and sound speed together, but sound speed is negligible. So
when you're doing scale-dependent things, though, you think the velocity dispersion changes with scale.
Yeah, it does change with scale, but we think that sort of so that's a resolution-dependent thing in our case, the way we measure it, because we measure the local velocity dispersion between like neighboring scales or cells, but that seems to correspond actually to these scales. So we think we are resolving the scale on which the disk becomes unstable, if that makes sense. I can talk to you about that in more detail because we did a study, but
Questions, I guess, is as a function of radius there,
yeah.
you're defining the block size, or is it, you know, we said 100 parsecs, what's the size of your grid cell? What is it at a tenth of a parsec?
So I think actually, so I have another plot where maybe we can infer that. Let's see. Okay, so here what we've done is to sort of measure the turbulence on a range of scales and to determine the scale on which our measurement of the turbulence sort of reaches the resolution limit. So that's what these points are. These are the scales where we reach our resolution limit, these points. But it's sort of to within a factor of 2 because when you're measuring amongst neighboring cells, you're limited by the cell size. So this isn't the most reliable estimate, but it sort of shows you where our resolution is in comparison to the unstable scales, which is what I was trying to say before. So does that kind of answer your question? Sort of? Okay. Okay, so coming back, just going to show you this time evolution movie. So this is on a scale of 250 parsecs, and here we're looking sort of face on into the circumnuclear disk. And so you can see the development of waves and instabilities and stuff moving in the disk. So these are mostly waves moving in the disk because the disk is rotationally dominated. So it is just mostly the gas is just going around in circles. But there is sort of a combination of things going on. There are sort of bits that fall in at some points. And here's what this looks like on a smaller scale, on a scale of 25 parsecs. And here we're closer in, so things are moving a little bit faster. But you see kind of a similar behavior, just sort of waves and things moving through the disk, except when this big blob comes in here. But okay.
What do you think they call it center? I mean, should we put around by its gravitational forces, right?
Yeah, but it stays in the center. I mean,
do you impose this, or
do we force it to stay there? No, we don't.
so that it just stays there?
Mostly, it stays there. Every once in a while, it wanders a little bit, like if something falls in. And I'll actually show, my last slide is the interior mass as a function of time. And on the smaller scales, you can see the point where the black hole sort of moves a little bit. It affects this number. So yeah, but on these scales, the location of the black hole, the movement is negligible. I mean, it moves like less than a parsec or something. So yeah.
So your mean density, at least for the ridges, is 10 to 7, 10 to 8.
Sorry, what?
The mean density in those ridges, spiral arms over there,
Yeah.
it's like 10 to 7 or higher.
Yes. Okay. So you might ask the question whether, so we've sort of examined the stability of the disk against linear perturbations, but you might ask whether nonlinear effects can become important. And this might be evident, for example, when you're looking at the Jeans length. So if we weren't resolving the Jeans length, then we wouldn't know necessarily if sort of nonlinear things are happening on smaller scales. So this plot is just to show, this is a scatter plot for individual cells in the disk, showing the ratio of the Jeans length to the cell size. And so where this number is greater than 1, we are resolving the Jeans length. And so the fact that the disk is locally stable seems to be fairly robust. At least we are resolving the scales on which nonlinear effects might also be causing collapse, but they're not. But there are some regions where we're not necessarily resolving, where we might be missing things, and the disk should be collapsing all the way and forming stars. And these may even correspond to resonances in the disk or something, but we haven't looked in great detail at that. That's something that we can do for sure. Later on, if we sort of do another run with more aggressive refinement in these regions. But as far as it looks like we're not, so we don't see the gas just catastrophically collapsing everywhere into these tiny clumps. And you can see that in this bottom plot here, which shows the distribution by volume of sort of the highest level of refinement cells as a function of radius. And all of the finest refined cells are in the center of the galaxy. We don't find little clumps, or not very many, forming out here. But one thing that we want to go back and do is sort of push the resolution in the outer parts of the galaxy, at least in like a ring or something, and see if that holds true with more aggressive refinement. But right now, it looks like there's no sort of widespread burst of star formation in the disk. So can sort of come up with, or you can sort of describe the situation with an analytic description. So here, this is just from conservation of angular momentum. This equation describes sort of the transport of angular momentum in a thin, azimuthally symmetric viscous disk. And so the left-hand side of this equation just describes advection of angular momentum through the disk. And on the time scales that we follow the simulation, there isn't much, right? Things are still going around in circles, and we don't see a lot of stuff falling in. So we think that angular momentum transport is happening on much longer time scales. So on these sort of shorter simulation time scales, this side of the equation is pretty small. And the right-hand side is this viscous torque term, which describes how viscosity can sort of generate this torque in the disk, which might cause angular momentum to move outward. But since we don't see a lot of angular momentum moving outward, this side is small, and we think also, therefore, that this gradient must be small. And so, sort of by dimensional analysis, we know how this gradient should scale, like this, and we can measure many of these quantities in the disk and derive sort of the slope of the profile of the density, for example. So in order to do this, we need to be able to measure the turbulent viscosity, this new parameter. So you can estimate the turbulent viscosity with a characteristic length scale and a characteristic velocity scale. So we tried using the fastest growing unstable mode and also the turbulent velocity, or in our case, just the velocity, the local velocity dispersion. So we used these two quantities to estimate the turbulent viscosity. And here it is as a function of radius. And we see that it is pretty constant in radius. So if you put that scaling, at least in the circumnuclear region, if you put that scaling back into this equation, then you expect to find, for the slope for the density profile, a slope of minus 8/3, which is what we measured when we measured our gas density profile. So this isn't necessarily a proof of anything. It's just a description of what we think is going on in the disk. And we think that what we measure is consistent with an interpretation where this sort of global instability develops in the disk, and this drives this sort of ensemble of shocks through the disk and waves and things moving through the disk that create turbulence, which maintains the local stability in the disk. And this viscous torque is what sort of maintains this quasi-steady structure and gives us this density slope over many orders of magnitude for a long time. And we also looked at the probability distribution function for the density in the disk. And often in highly supersonic turbulent molecular clouds, you measure this log normal PDF as a function of density here. So we measured a PDF for our simulation, and this is sort of a time average version, sort of at a typical radius in the disk. And we find that ours also follows this log normal distribution, at least over a few orders of magnitude. So that seems to also be consistent with supersonic turbulence. Sorry, what? The width?
The sigma squared is asking.
What is the sigma? Oh, I'm not sure. I think it was like, from the plot, I guess you can kind of tell, but I think it was like, 2, in log scale, it was like 2 or something. I don't remember. I have it written down somewhere. I can let you know, but yeah. Okay. So sort of as a last point, so this is all kind of stuff that we were doing, and now we're at the moment looking at gas accretion in the disk. So this is sort of the thing that, everybody who works on AGN and black holes, when we tell them what we're doing, they want to know what the gas accretion rate is. And it turns out that, at least in our simulations, it's not such a simple number to give. So what this is, on the left-hand side, this is the interior gas mass as a function of time in our simulation. So here, this is where the simulation is now, or it's a little further, actually, but this is the most recent plot. And these are at several different radii. Here's the legend here. So this is the 0.1 parsecs, and this is 1,000 parsecs. And here, when I mentioned before that the black hole does move a little bit in the center, that's what this blip here refers to, because we measure all of these numbers with respect to the black hole location because it's supposed to be marking the center of the galaxy. So here, when the black hole moves, it disrupts this innermost mass profile. Yes. So what we find is that, well, there's no there's no obvious trend in mass accretion over this time scale. And to demonstrate that, we took a power spectrum. So it's basically the square root of the power spectrum, but it's the amplitude of a sine wave of the mass in Fourier space, basically. And we find that the slope of these power spectra is approximately -1. So this is corresponding to 1 over F noise, which means that at least over this time, we don't find any preferred time scale for accretion. And you can this is just sort of confirming what you see when you look at this, that there are no obvious cycles for accretion on the scales over this time, which maybe isn't surprising. No, we don't allow it to grow. So there is, I think, this particular zoom-in episode took place at redshift 4, which we chose to avoid mergers. We wanted to start in the most simple case. So there are no major mergers going on, but I think it is fairly recent to a minor merger. But I'm not sure where in the disk the minor merger is at this point. So there is a minor merger sort of in the recent history. So one thing that I didn't mention earlier on when I was talking about this zoom-in method, but sort of the advantage of it is, well, one, we have a cosmological simulation that we're starting from, so we have all these different redshifts, so we can sort of do this to study many different activities in the lifetime of this galaxy. So in this case, we chose a relatively quiescent stage of evolution, although it's still active because the galaxy is still growing really fast. But you can also use this technique to go back and follow mergers, for example.
So that's like 1 million years? The whole length of those curves are 1 million years?
Almost.
And so that is the Neanderthal timescale at what radius?
So 500,000 years is about 100 parsecs, I think. So 100 parsecs, the disk has gone around once, and the dynamical time is close to the rotation time. So at about 100 parsecs, we've resolved one rotation period. So, yeah. So this 1,000 parsec curve is not that meaningful, but over this time scale, you wouldn't expect that anyway.
These are much higher densities than any real galaxies ever reached. Like to have 10 to the 10 solar masses inside 100 parsecs. That's denser than the densest subnodal galaxies, and way denser than any of those.
Yeah. So that's true, and I'm not sure in that way how to fit what's going on in this galaxy into real context, because I know that it's a problem in simulations that you often develop these very massive sort of central.
So you have no feedback by the central massive black hole or anything else? Well, there's still star formation that's injecting energy. No.
Yeah.
So you have the star formation too, so there's no feedback at all.
So again, this is starting simply. So the goal is to add these things. So we're adding, actually, this is for the next current and future projects. So, so we mentioned adding optically thick cooling to the gas, which I think is really the first thing that we need to do to even start to do all of these other things, right? Because it's important for everything. But with that, we can do the formation of the obscuring torus, or we can at least try to see, what the structure is in the region where we expect to find the torus, and then relate that to an AGN when we put that in. We can also study feedback, which is the next sort of big thing that we want to do with this simulation. So we have to turn stellar feedback back on because it is important in real galaxies and their evolution. And that may affect this central density concentration that we find. So we may start to get more realistic things when we put in feedback. So we want to put the stellar feedback back in, but we also want to model AGN feedback. And because we have this really high resolution, we can model different kinds of AGN feedback and different geometries, and we can play with efficiencies and all this stuff. So all of these open questions with AGN. And we can sort of model those side by side with the stellar feedback and make comparisons between the contributions of the two inside the galaxy, but also sort of on supergalactic scales where these are also thought to have effects, but it's not clear, where the dominant effects are. Also, star formation is a big thing. So I didn't talk a lot about what our actual prescription for star formation is, but it was written to go with a cosmological code. So if we're evolving this thing on really short timescales, our star formation recipe isn't going to give us the most reliable things. So when I was talking about there's no widespread burst of star formation in the disk, we're just measuring what we expect to be happening in the gas. But the actual star formation prescription needs to be sort of modified for this high resolution run if we're going to do things like include stellar feedback on the very high resolution scales. So we can sort of improve our prescription for star formation and try to follow things like nuclear starbursts and also resonances, which is something that I mentioned before. We want to go back and sort of look at different regions of the disk with high resolution to see if we're sort of getting these resonances that you might expect to find during secular evolution of galaxies when gas is piling up and then fragmenting into stars. And then sort of farther into the future, the next sort of big project that we want to do is to follow mergers. So what we can do is to just sort of extend the current study and follow matter transport and include the feedback in this case in more than one galaxy. So instead of just resolving the central galaxy with this great resolution, we can also resolve a second galaxy and follow them as they merge together. So this is important in the context of sort of galaxy formation and cosmological scales and stuff, but it may also provide interesting results for things like the importance of nuclear disks for black hole mergers. So there's this idea that one way that you can get around the lost cone problem, whereby stars that are sort of taking away energy from the black hole so that they can merge together, sort of you have this lost cone where stars are getting depleted away and then you don't have this mechanism for taking away energy from the black hole to bring them together. But if you take this whole scenario and put it inside a nuclear disk, the disk can have a great effect on, well, first what happens to the stars, but also how the black holes merge together. And then ideally, sort of in conjunction with all of these things, but I put it under mergers because I think it's the best thing for mergers, I want to run a larger version of this simulation to get sort of a bigger population of galaxies. Because right now, I'm just talking about one kind of galaxy in the history of this one disk galaxy as it goes through mergers and evolves with time. But we'd like to have maybe even a cluster where we can follow the physics in more detail. So I'll just finish with the summary. Sorry. Yeah.
So could you describe your star formation description? And if you did use it, what would the star formation rates be in the case?
Yeah, I can. Okay, so the way that star formation is done is that basically if a cell has a low enough temperature and a high enough density, then it forms stars. But there has to be some delay involved in order to match the global star formation rate, which is how the star formation rate or prescription was set up. So actually, a cell that forms a star can't form another star for like another 20 million years or something. And our simulation, we only ran for 1 million years so far. So at this scale, we don't even, I think we formed something like, 50 stars or something over the duration of the simulation, and none of them are in the circumnuclear region. I don't think. I'm not completely sure, but.
Stars are discrete?
They are, yes.
Star particles, the stellar cluster, they're stellar classes, or they're not, you don't simulate a single star.
No. Yeah. I think the smallest stellar particle is like 1,000, maybe it's a few hundred solar masses. So it's supposed to represent a bunch of stars.
Number density inside your cell. And you turn its efficiency one to turn into stars, you have to turn the efficiency down.
So that all the gas turns, you mean? I think it's just, actually I'm not sure what the number is, but it's not one, it's less.
So you a cell crosses some threshold and forms a bunch of stars, and then you say that it can't do it again for a while.
Yeah. And it also, in the cosmology simulation, when it does that, it also produces feedback. So there are two different runs. I think one where the feedback is delayed and one where it wasn't. And I think I use the one without the delay, but I think there's not a big difference between the two.
And
so.
you tune the numbers to get the Kennebec law?
Yeah. Supposedly, it follows a Kennebec law over cosmological times, or on large scales, I mean. But that's obviously not adequate for the high resolution part of the simulation because, well, we don't even really know what it should be. Right, it's a constraint, yeah. Question?
Yeah, so when you say you're resolving the genes, like, it was hard to tell from the plot, what fraction are you resolving, what fraction of your cells are resolved, you know, say 10 genes lengths? Because if they're much fewer, right, then you can still get.
That's true. So the sort of, I think the kind of standard criterion that people use, well, as a resolution criterion is you have to resolve, well, for AMR codes, it's like four cells or something. So this number should maybe not be 1. It should be more like 4. But that's still, most of the cells are above that. It is hard to tell, but I think they're pretty isotropic over this. Yeah. Yes?
You mentioned you want to study the AGN feedback in your future projects.
Yes.
Starting then from some cosmological snapshot that did not include AGN feedback up to this time. So how consistent is this? That if you switch on this very high resolution prescription, we follow it for a couple of, say, 10 to 6 years.
Yeah.
And you can't really feedback this, or there might be the earlier AGN feedback might have a big impact on the current distribution of mass and so on.
Well, I think maybe we'll be able to estimate how significant that effect might be if we do this at several different redshifts. So if we put in AGN, I mean, we know when we're supposed to have AGN in the universe from like the peak of the AGN luminosity function. But I think that maybe if we look at different redshifts, we can sort of. I guess if we start doing this at really high redshift and they have this really big effect, then maybe we do need to account for that somehow at lower redshift as well, is what I mean. So, yeah. Yes?
It's kind of related, but so your rotational velocities were thousands of kilometers a second.
Yes.
In the regions, which I assume is because you have such a high density gas system that you don't actually see
Yes.
in the universe. And I guess that you build that up, you don't start off like that, you build that up when you do these higher and higher refinements.
Yeah, I think so. I didn't actually look at the rotational velocities during the zoom in to see that that's true, but that sounds true. So
in
yeah.
that case, you're going to have things like your instability criteria, which depend on, for example, the rotational kinetic energy, which
Yeah.
is much, much higher there than would be in a realistic case where the feedback is actually preventing you from getting these ridiculously high densities in the center.
That's true. So that's something that I hadn't looked into. That's probably worth looking into, going back and looking at the zoom-in process to see what happens along the way. So yeah, I haven't done that, but that's a good idea.